Course code is CS430 and course title is Microprocessor Programming and Interface. Before we start our today's lecture, a brief review of the previous lecture is present. We have discussed following microprocessor pins in addition of the evolution of microprocessor and introduction to the microprocessor. We have discussed VCC pin and ground pins of microprocessor. That means we have discussed power pins of microprocessor and we have discussed minimum maximum pin. Then we discussed address data multiplex bus for 808 microprocessor as well as uh, address data multiplex bus for 8086 microprocessor. After that, we discussed dedicated address lines address bus for 808 microprocessor. Then we discussed address status multiplex bus for both 8088 and 8086 microprocessors. And in connection with the demultiplexing of address from data and status, we discussed ALE pin address latch enable for both of the microprocessors 8088 and 8086. And we discussed DEN bar data bus enable pin and DT slash R bar data transmit slash receive pin in connection with the buffering of the data bus for both microprocessors 8088 and 8086. In this lecture, we have to cover following minimum mode operation pins for 8088 and 8086 microprocessor. First of all, we will be discussing the clock signal for required for operating 8088 and 8086 microprocessors. Then in connection with clock signal, we will be discussing reset signal and ready signal. Then we will be discussing taskbar pin, read bar pin and write bar pin. And for microprocessor 8088, there will be IO/M bar pin, and for 8086, there will be M/IO bar pin. Then we have to discuss interrupt pins present on the IC package of microprocessors 8088 and 8086. INTR interrupt request, INTA bar interrupt acknowledge pin, and NMI pin non maskable interrupt pin. After that, we have to discuss hold acknowledge. Hold pin is for DMA request and HLDA pin is for DMA acknowledge. Then we have to discuss status pin SS not bar for microprocessor 8088. In case of 8086 microprocessor, in place of SS not bar, there will be BHE bar pin /S7. Then there will be a table of current state of microprocessor 8088 when it is operating in minimum mode, and that table is made by using IO/M bar, DT/R bar and SS not bar pins of 8088 microprocessor. Then status signals for 8088 microprocessor will be discussed. There are 4 status signals S3, S4, S5 and S6. In case of 8086, there are 5 status signals S3, S4, S5, S6 and S7. So these status signals will be discussed in this lecture. So first of all, we have to discuss the clock signal to be applied at clock input of 8088, 8086 microprocessors. The basic version of both of these microprocessors require A 5 MHz clock input of 33% duty cycle. 33% duty cycle means the square wave applied at clock input should be having on timing 33% of the total time period. If you are applying 5 MHz clock input, then the time period for one clock state will be 200 nanosecond. Now we come to the second input pin, that is reset input. If you want to reset microprocessor, a logic 1 is to be applied at reset input for at least 4 times the T clock. If you are applying 5 MHz clock at clock input, then T clock is 200 nanosecond. So that means to reset microprocessor 8088, 8086 at reset input, you should be having logic 1 for at least 4 times 200 nanosecond, that means 800 nanosecond. After resetting, microprocessor will be generating address FFFF0H, and that is called cold start address. And whenever microprocessor is resetted, interrupt flag becomes 0. After that, we have to discuss ready pin. Ready pin is also another input pin for 8088, 8086 microprocessors, and a timing diagram is shown here in connection with clock input. So timing requirement is that ready pin is checked at the end of T2 for each and every bus cycle. If ready pin is having logic 0, then microprocessor goes into wait states. During wait states, ready signal is checked in between of the clock. If in between of the clock ready pin is 0, then next pulse will also be a wait state. Otherwise, wait state will be ended and you will be having T3. So for the time being, we have to remember that ready pin is used to insert wait state in the timing of microprocessor if more time is required to access memory devices. In this slide, we have discussed operation of test bar input pin for microprocessor. In the instruction side of microprocessor, there is an instruction wait instruction. Whenever wait instruction is executed, first of all, it will be checking the logic level of test bar input. If test bar input is having logic 0, wait instruction will be executed as NOP instruction. Or otherwise, if test bar input is having logic 1, then microprocessor waits for test bar pin to become 0. Or you may say that the instructions present onward to wait instruction will not be executed unless test bar pin becomes logic 0 when there is an wait instruction in your program. So test bar pin checks the readiness of a hardware. It may be a coprocessor or a simple hardware. Next pin is read bar pin. Read bar pin is an output pin. That means processor 8088 or 8086 will be generating that signal. So whenever microprocessor is performing a read operation from memory or IO, read bar pin will be at logic 0. Otherwise, read bar pin will be at logic 1. Next pin is write bar. Whenever microprocessor will be performing a write operation to any memory device or an output device, then microprocessor will be placing this pin at logic 0. When write operation is not to be performed, then write bar pin will be at logic high 1. Then we have to discuss operation of IO slash M bar. IO slash M bar is a pin present in 8088 microprocessor. This pin differentiates whether microprocessor is going to access memory or IO device. If microprocessor places this pin at logic 0, that means the generated address is for memory device. Or otherwise, if IO slash M bar pin is having logic 1, then the generated address is of an IO device. So this pin is used to to identify that microprocessor is going to access a memory or IO device. In case of 8086 microprocessor, in place of IO slash M bar, the signal becomes M slash IO bar. So for memory access, processor 8086 will be generating logic 1. For accessing IO device, processor 8086 will be generating logic 0 at pin M slash IO bar. In this slide, we are going to discuss min slash max bar pin, that is an input pin for microprocessors 8088 and 8086. This pin is used to select minimum mode operation or maximum mode operation for your system. In minimum mode operation, you will be having a single processor, that is microprocessor, and in maximum mode, you will be having more than one processors. In addition to the microprocessor, you will be having some coprocessor attached in your system. So if you apply logic 1 at minimum maximum pin, you are working with minimum mode. Or otherwise, if you have connected this pin with ground, then you have selected maximum mode operation. Then we have to discuss pins related to the interrupt present on the package of 8088 8086 microprocessors. First pin is INTR, interrupt request input. Interrupt request pin may be enabled or disabled by using interrupt flag, and logic label of interrupt flag may be changed by using some instructions. So if you have placed interrupt flag at logic 1, then INTR is enabled, or otherwise if you have assigned interrupt flag at logic 0, then interrupt request pin is disabled. When you have placed interrupt request pin in enable state, then whenever a logic 1 is appeared on INTR pin, that that means an IO device or more than one IO devices have placed their interrupt signals on INTR pin. And if there is a logic 0 at interrupt request pin, that means no interrupt is present from IO devices. Then the response of INTR is generated on the pin INTA bar, interrupt acknowledge pin. That is an output pin. So if INTR pin is in enable state and a logic 1 is appeared on INTR pin, microprocessor will be responding to that interrupt request and will be placing logic 0 after some time at INTA bar. Detailed operation of interrupt request and interrupt acknowledge pins will be discussed in interrupt chapter. Now we have to discuss NMI pin, non-maskable interrupt pin. That is another input pin, and this pin is independent of the interrupt flag, logic level of interrupt flag. Whether interrupt flag is at logic 1 or 0, NMI pin will be in working condition. Operation of NMI pin is similar to INTR. A request will be appearing when NMI pin is at logic 1, or in case of logic 0 at NMI pin, there is no interrupt present. Uh, Difference with INTR is that the interrupt vector is decided for NMI pin, and interrupt vector 2 will be used for servicing the interrupting device, IO device. While in case of INTR, there is some other method to get interrupt vector number. The concept of interrupt vector will be discussed in the chapter interrupt. In this slide, we are going to discuss DMA related pins present on the package of microprocessor 8088 and 8086. Hold pin is to receive DMA requests from IO devices, and the response of those DMA requests will be generated at HLDA output pin by microprocessor. So if an IO device wants to place DMA request, it will be placing logic 1 at hold input of microprocessor, and microprocessor will be giving control of the buses to the DMA controller by placing HLDA pin at logic 1. So detailed operation of hold and HLDA pins will be discussed in DMA chapter. Then we have to discuss SS not bar pin, that is 8088 microprocessor pin. This pin is called an status pin, and that is an output pin. In conjunction with IO/M bar and DT/R bar, this SS0 pin shows the current state or bus cycle of 8088 microprocessor. The table for that state of 8088 microprocessor is present in the next slide. Then we have to discuss operation of BHE bar slash S7 pin of microprocessor 8086. BHE means bus high enable. As we know that data bus is of 16-bit for 8086 microprocessor, and that data bus is multiplexed with address. So we are having 8002 8015 address data multiplex bus in case of 8086 microprocessor. So whenever microprocessor wants to communicate with external devices, memory or IO by using 88 to 8015 data lines, higher 8 bit of data lines, then BHE bar will be at logic 0, or otherwise if higher 8 bit of data are not to be used, then that pin will be at logic 1. In this slide we are going to discuss a table in which we are having three microprocessor age-rated pins. First one is I/M bar, second pin is DT/R bar, and third pin is SS0 bar. This table shows the current state or bus cycle of microprocessor age-rated. So as there are three microprocessor pins, so 8 different patterns are possible. So there are 8 entries in this table. So in the rightmost column you are having operation of microprocessor. If there are 000 at I/M bar, DT/R bar and SS0 bar, then microprocessor is executing opcode fetch bus cycle. In case of 001, microprocessor is executing memory read bus cycle. In case of 010, microprocessor is currently executing memory write bus cycle. Then in entry number 4, 011, there is an state of microprocessor that is called halt state. That is not a bus cycle. Then from 5 to 7, fifth entry is 100, and 100 means interrupt acknowledge bus cycle, and so on. 101 means microprocessor is currently executing IO read bus cycle, and 110 means microprocessor is currently writing data to an output device, or you may say that IO write bus cycle is in executing. And the last entry is 111. That means microprocessor is in passive state. That is not a bus cycle. So in this table there are 6 bus cycles: opcode fetch, memory read, memory write, IO read, IO write, and interrupt acknowledge. And there are 2 states. First one is halt state and second one is passive state. Detailed operation of these bus cycles will be discussed later in coming lectures. Uh, for the time being, we are going to discuss IO/M bar and DT/R bar and SS0 bar for these bus cycles. Opcode fetch bus cycle will be bringing decodable data from memory, and that will be an instruction opcode. So you are going to access memory during opcode fetch bus cycle. So IO slash M bar is having logic 0 and data will be received by microprocessor. So DT slash R bar is having 0 and SS naught bar is 0 for opcode fetch bus cycle. The only difference between opcode fetch and memory read bus cycle is that SS naught bar is having 0 for opcode fetch, but there is a 1 at SS naught bar for memory read bus cycle. Because during memory read bus cycle, memory will be accessed, data will be received by microprocessor, but that data will not be a decodable data, but that will be a simple data, or you may say non-decodable data. Detailed will be discussed in later lectures. For memory write bus cycle, you are having 0 at IO slash M bar because memory will be accessed, and during memory write bus cycle, data will be transmitted by processor towards memory device. So DT slash R bar will be having logic 1 and SS naught bar is 0 for memory write bus cycle. To differentiate between memory write bus cycle and hold state, SS naught bar is 0 for memory write bus cycle and for hold state SS naught bar is 1. Remaining two signals IO slash M bar and DT slash R bar are the same for memory write and halt. Now I am going to discuss second half of this table starting from interrupt acknowledge bus cycle. During interrupt acknowledge bus cycle, IO device will be accessed. So IO slash M bar will be having 1 and data will be received from IO device by a microprocessor. So DT slash R bar is having 0 and same operation of receiving data by a microprocessor from IO device will be performed during IO read bus cycle. So IO slash M bar is 1 and 0 for both of these bus cycles. But SS naught bar is 0 in case of interrupt acknowledge bus cycle, while in case of IO read bus cycle, SS naught bar is 1. During IO read bus cycle, data present at input device will be received by a microprocessor, while in case of interrupt acknowledge bus cycle, the number of input device will be received by a microprocessor. You will be assigning a particular number to each and every input device and output device in your system. So during interrupt acknowledge bus cycle, that particular number will be received. So SS naught bar will be differentiating between interrupt acknowledge and IO read bus cycle. The detail of interrupt acknowledge bus cycle will be coming in interrupt chapter. The second last entry in this table is IO write bus cycle. During IO write bus cycle, IO is to be accessed by microprocessor and microprocessor has to output data to an output device. So microprocessor will be transmitting data through data bus and SS naught bar is 0 for IO write bus cycle. In case of showing passive state of microprocessor, SS naught bar is 1. Remaining two entries IO slash M bar and DT slash R bar are same for IO write and passive. Both are 1 1. Detailed timing diagrams for these 6 bus cycles will be shown in next lecture. And what are these states, passive and hold state? In hold state, microprocessor will be doing nothing, and to enter into a hold state, an instruction will be executed by a microprocessor. Instruction is HLT. HLT instruction, whenever microprocessor executes HLT instruction, microprocessor enters in hold state, and microprocessor will be there in hold state, will be doing nothing, will be in an idle state until you force microprocessor to come out of the hold state. There are three operations that may be performed to bring out the microprocessor of the hold state. First one is to reset microprocessor. Apply a 1 at reset input. Second method is to place an interrupt request at INTR pin. Third method is to place a DMA request at hold input of microprocessor. So by doing any one of these three operations, microprocessor may be brought out of the hold state. And now passive state. Passive state is the state in which microprocessor will be performing some internal operations, but there will be no operation external on the buses. That means microprocessor will not be using address bus, data bus, and control signals, but microprocessor will be operating internally. For example, microprocessor has to perform some shift operation multiple times. So during that shift operation, nothing will be performed on the buses, but microprocessor will be shifting a number in its ALU for some time, and during that time there will be no operation on the buses of microprocessor. So that state will be called passive state. In this slide, we have to discuss status signals for microprocessor 8088 and 8086. There are 4 status signals for 8088 and 5 status signals for 8086. There is a table shown in this slide for S3 and S4 status signals. This table shows that microprocessor is accessing which segment. During memory access, microprocessor will be accessing some segment. There are 4 types of segments: extra segment, stack segment, code segment, and data segment. So whichever segment is accessed during the current bus cycle, according to that, S3 and S4 will be having logic levels. So if microprocessor is accessing code segment, then 10 will be appearing on S3 and S4. If microprocessor is accessing data segment, 11 will be appearing on S3 and S4. In case of stack segment, 10 will be present at S3 and S4. In case of extra segment, 00 will be present at S3 and S4. And what is the meaning of no segment? As you can see that with code segment you are having code or no segment. That means microprocessor is in passive state. Microprocessor is accessing no segment, but it is working some calculation or shifting or rotation operation in its ALU. So there is no access of memory, but microprocessor is working internally. So S3 and S4 will be having 0 1 respectively. Next status signal is S5. S5 shows the logic level of interrupt flag. If interrupt flag is having logic 0, then S5 will be having logic 0. If interrupt flag is at logic 1, then S5 will be at logic 1. S6 will always be at logic 0, and S7 will always be at logic 1. So what is the purpose of S6 and S7? If you are having S6 for any microprocessor as logic 1, so that means your processor chip is not working well. That may be a faulty IC, faulty microprocessor. Same is the case for S7. If you are receiving S7 as logic 0, then your microprocessor may be a faulty one. So these are the status signals of processor 8088 and 8086.